The work we present today is about developing a surrogate-based framework to efficiently perform uncertainty quantification analysis for both linear and nonlinear thermoacoustic instability predictions. This work was done by me and other coworkers in TU Munich. To predict thermoacoustic instability, a popular way is to use an acoustic solver like a high-mode solver, combined with a flame model and the proper acoustic boundary conditions. For linear case, for example, we have flame transfer function FTF, and the output of interest are the model frequency omega and the growth rate sigma. For nonlinear case, we may have flame describing function FDF, and the output of interest are the limit cycle frequency omega and the limit cycle amplitude A. In practice, it is often the case that our flame model parameters or acoustic boundary conditions are uncertain, which are usually described by probability density functions. Due to those input uncertainties, our output will not be deterministic, but rather stochastic. In order to quantify this output uncertainty, we usually perform Monte Carlo simulations. Simply put, we draw samples from those input PDFs, and we calculate their corresponding eigenvalues to get their distributions. This is an expensive approach since the required sample size is this huge, and running acoustic solver this many times is just not practical. So to reduce this computational burden, we could employ surrogate modeling technique. The idea is simple. We carefully select some samples of flame and acoustic parameters and use acoustic solver to calculate their corresponding model eigenvalues. Based on this training dataset, we can train two surrogate models, which take in flame and acoustic parameters and output the approximated model frequency and growth rate values. Once the surrogate models are trained, we can apply Monte Carlo directly to those surrogate models to obtain the same output distribution. Since surrogate model is very fast to evaluate, this technique can significantly improve the efficiency of the UQ analysis. Although sound attractive, building surrogate models is not necessarily an easy task. This is because the so-called curse of dimensionality, which states that the required number of training samples grows exponentially as we have more input parameters. In practice, however, flame models usually have many parameters. For linear case, for example, we may use a flame impulse response model, which describes flame dynamics in time domain. Those model coefficients, HK, usually identified from noisy CFD simulations with limited time series data, are uncertain. This type of model usually contains 30 to 70 coefficients. Therefore, the training effort of building surrogate models for FIR model will be much higher than, say, build a surrogate model for n-tau model, which only has 2 parameters. For nonlinear case, the situation is even worse as we are using a flame describing function. Each data points in gain phase measured at discrete frequency and forcing amplitude constitute an input parameter that we need to consider. The corresponding training effort would be prohibitive in practice. Now the question is, can we develop a new surrogate scheme to flatten this curve and effectively break the curse of dimensionality? That's exactly what we are trying to answer in the current study. The remaining of the presentation goes as follows. I will start with introducing our big idea, the surrogate-based scheme for thermoacoustic UQ analysis. Our strategy will be based on Gaussian process, which we will briefly talk about in the next part. Later on, I will apply the proposed surrogate strategy to address 2 case studies. One linear case where we consider an uncertain flame impulse response model, and a nonlinear case where we consider an uncertain FDF dataset. Okay, so let's start with the strategy. Consider flame model as a transfer function. Its role is to take in model frequency and the growth rate and output the flame gain phase. Meanwhile, acoustic solver can input flame gain phase as well as the acoustic parameters and output the frequency and the growth rate values of the mode under investigation. By coupling those 2 components, we can form the so-called thermoacoustic eigenvalue problem and solve it using iterative schemes. The evaluation of this part is usually very slow, as it usually involves implementation of expensive numerical schemes, like finite element method. Now imagine if we can build surrogate models to approximate this slow acoustic solver. Those 2 surrogate models will take in flame gain phase and some acoustic parameters and immediately output the model frequency and growth rate, respectively. Then, by linking together those two parts, we can now use iterative schemes to calculate thermoacoustic modes. Since those two surrogate models are just algebraic models, this iterative scheme to solve the eigenvalue problem will be much faster than using acoustic solver. In the current study, we choose Gaussian process as the surrogate model. So Gaussian process is a Bayesian learning method. It assumes that the function we are trying to approximate is a realization of Gaussian process, which is characterized by a mean function that describes the general trend and a covariance function that describes the spatial correlation. Usually, the mean is some unknown constant, and the covariance function or kernel function usually looks like this. By using the training data, we can estimate the values for this constant beta, sigma square, and theta that best fit the data. Then we arrive at the posterior, which gives us the mean value at an arbitrary location x and its associated prediction uncertainty. This uncertainty estimation is critical. In the current study, we use this information to determine where to allocate our next training samples to refine the GP model. This adaptive way of training is much more efficient. Okay, so now let's move on to the case study part. First up, the thermoacoustic problem settings. For the configuration, we use EM2C burner configuration 11. We use Helmholtz solver as our acoustic solver to generate training samples. So our Gaussian process models will have the same fidelity as the Helmholtz solver. And we focus on the first longitudinal thermoacoustic mode. For our current problem, we aim to train two GP models to approximate the frequency and growth rate of the investigated mode. The GP models are built upon 5 parameters, flame gain phase, and 3 acoustic boundary conditions, reflection coefficient at inlet Rin, at outlet Rout, and the system acoustic damping term alpha. The ranges of interest are summarized here. We choose rather large ranges for gain phase because we want our GP models to be as general applicable as possible. For system acoustic damping alpha, its uncertain range is determined according to the work of Silva. In total, we used 150 samples to train those two GP models. We actually start with only 50 samples, then we gradually add more samples to refine the GP models. Detailed adaptive training scheme can be found in our paper. So at this point, we have two GP models ready. Let's put them into use to address a linear case study. Here we consider a flame impulse response model. This model describes the flame dynamics in time domain, and it can be easily converted to a flame transfer function that's facilitating thermoacoustic instability calculations. Our current model is identified by applying system identification method on the time series of velocity fluctuation and the flame heat release fluctuation. Due to the combustion noise and the limited time series data, the identified FR model coefficients are uncertain, represented by the confidence interval here. The resulting FTF uncertainty is shown here. In total, we have 65 uncertain coefficients, which follow a multivariate normal distribution. Our goal is to propagate those uncertainties to the frequency and the growth rate predictions. We use the surrogate-based scheme we discussed earlier to do the UQ analysis. So in addition to the uncertain flame parameters, we also consider Rin, Rout, and alpha, these 3 uncertain acoustic parameters. In total, this is 68-dimensional UQ problem. For each sample of impulse response coefficients and Rin, Rout, alpha, we perform this iteration loop. In total, we used 20,000 samples to perform Monte Carlo. Here are the results. We compare the PDF predicted by GP-based scheme and directly Helmholtz calculation. For both frequency and growth rate, we have achieved very good match. In terms of computational time, almost 20 times faster is achieved. Okay, so much for the linear case. Now let's see a nonlinear case. So we're still using the same GP models we trained earlier. This is also one of the benefits of the proposed scheme. We can use the same GP models to solve multiple problems. Everything is the same as the linear case, except now we are using an FDF model. This is the measured data of FDF. We don't have the measurement uncertainty of those gain phase data points, but we will use those data points as the base to generate uncertainty. So this is the experimental data. In total, it measured 6 acoustic oscillation amplitudes. And for each amplitude level, it measured gain phase values at every 10 Hz. In practice, FDF data uncertainty is induced by limited data quantity and data quality. We can only measure FDF gain phase at limited amplitudes and frequencies. That's data quantity issue. And those measurements are not perfect. They have measurement error. That is the data quality issue. To mimic this uncertainty generation process, first step, we only use measurement data at these frequencies. Second, we assume for gain at each measurement location, the measurement uncertainty follows a normal distribution, with the mean being the original experimental value, and the standard deviation being 10% of the mean. For phase, we also assume measurement uncertainty at each location, which also follows a normal distribution with the mean being the original experimental value and the standard deviation being 5% of the mean. To facilitate limit cycle prediction, we need to interpolate those data to a finer grid, which in our current study we use 10 levels of amplitude and 26 levels of frequency. Since those data are uncertain, when we do the interpolation, all those 260 data points for gain and another 260 points for phase, they are all uncertain. Now our goal is to propagate those uncertain FDF dataset to the limit cycle calculations. To do that, for each FDF realization, we calculate the modal frequency and the growth rate for each amplitude level. We use MATLAB rational fit to fit a rational function to approximate the discrete frequency response data. This gives us the flame model we need, which can be inserted into either Helmholtz solver or the proposed surrogate-based scheme. We repeat this process 10 times. Based on obtained trajectory of the growth rate, we can determine when limit cycle happens. And we use the corresponding modal frequency and acoustic perturbation amplitude as the limit cycle frequency and amplitude. Okay, now let's use the proposed scheme to do uncertainty quantification. So we have 260 uncertain data in FDF gain and 260 uncertain data in FDF phase, plus R in, R out, and alpha, these 3 uncertain acoustic parameters. In total, this is a 523-dimensional UQ problem. Okay, for each sample or realization of FDF, R in, R out, and alpha, we perform this 4 iteration loop 10 times, since we have 10 amplitude levels, to predict limit cycle frequency and amplitude. And in total, we use 20,000 samples to perform Monte Carlo. Here are the results. We calculate the PDF of the limit cycle amplitude and frequency. We can see very good match between two methods. In terms of computational time, 15 times acceleration is achieved. Also shown in the figures are the experimentally measured limit cycle amplitude and frequency, as well as the numerical results predicted by the AVSP in this paper. We see that both AVSP results and experimental results are covered by the predicted distribution. Therefore, we could argue that this mismatch may be attributed to the uncertain FDF data and acoustic boundary values. Okay, to summarize our current work, we developed a Gaussian process-based scheme to perform high-dimensional uncertainty quantification for thermoacoustic instability analysis. The proposed scheme can effectively break the curse of dimensionality, therefore significantly improve the efficiency of the UQ analysis. We further demonstrate the accuracy and efficiency of the proposed procedure by solving 2 UQ studies, one for linear case and one for nonlinear case. The proposed surrogate-based scheme has opened up several other possibilities. For example, we can calibrate input parameters like R in, R out, and alpha from experimental limit cycle measurements by using Bayesian analysis. We can also perform global sensitivity analysis to understand, for example, if flame uncertainty or the acoustic uncertainty contribute more to the variations of a limit cycle property. Also, we can do robust design to prevent limit cycle given flame uncertainties. That's all for the presentation. Thank you very much for your attention.